This is the fourth part explaining this slides about relations. We already discussed the definition of a relation, the domain and range of a relation, the inverse of the relation, and here we will speak about composition of relations. For the definition, let R be a relation from a set A to a set B, and let S be a relation from a set B to a set C. Note that the relation R is to the set B, while the relation S is from the set B. Then the composition of the relation R and the relation S is denoted by S circle R. Is you take all the pairs A and C, where you can find B in the set B, such that the pair A, B in the relation R, while the pair B, C in the relation S. Note that by definition, the relation S circle R is a relation from A to C, and this relation is done through the set B. So we take all the elements A, C, such that you can find an element B such that A is related to B under the relation R, and then B is related to C under the relation S. So let's state this definition in a simple example. So here we have my set A contains 5 elements from 1 to 5. B is also 5 elements, B, Q, R, S, and T, and C is the 4 elements, X, Y, Z, and W. And I define the relation R. It is from A to B, from the set A to the set B, by taking the pairs 1B, 1Q, 2Q, 3R, and 4S. And we define this relation S from the set B to the set C by taking all the pairs BX, QX, QY, SZ, and TZ. Then I want to find the composition of R and S, so I am taking S circle R, which results these 5 pairs of elements. So why we have 1x? We have 1x because 1 is related to B, 1 is related to B, and B is related to X. So the pair 1x is in this set. And also we have here 1 is related to Q and Q to X. So 1 and X is in this set, but it is the same element, 1x. And now we have 2 related to Q, and here we have Q is related to X and Q is related to Y. So these 2 pairs give me 2x and 2y. And 3 is related to R, but R is not in the second relation, so it will not give me anything. While 4 is related to S, and S is related to Z, and this gives me the element 4Z. And by this way, I find my relation S circle R. Since my relation R and S are finite, I can represent them by using the arrow diagram. So I will use these arrow diagrams to also illustrate how to find the composition of these two relations. So, for example, we have here the element 1 is going to B, and from B, under the relation S, it will go to X, and this gives me the first entry in the composition, which is 1x. But also 1 goes to Q, and Q is related to X and to Y. This gives me 2 elements, 1x, which is actually is here, and also we have 1 and Y, which is the second element here. For 2, we have 2 goes to Q, and there's a relation R, and Q goes to X and Y. So we get two elements here, 2 to x through q and 2 to y through q, and this gives me these two elements. Now 3 goes to r and there's a relation r, but r doesn't go to any, it's not related to any element in C, and there's a relation S. So this element will not give me any contribution in the composition of these two relations. While we have here 4 goes to S and S goes to Z under S, so we get the element 4Z. Now T to Z will not contribute to my composition, and that's because there is no element in A related to 2 under the relation R. So we find 5 elements in the composition of these two relations using the arrow diagram. Let's take another example of finding composition of relations, but this time we take the relations which are infinite. So I defined my relation S1 from the real numbers to the real numbers. It contains all pairs x, y, where the second pair, which is y, is equal to minus 5, x, which is the first coordinates, plus 2, and defines the relation S2 is taking all the pairs x and y, whereas the second coordinates y is equal to the first coordinates x square plus 2. I want to find the composition of S2 and S1 and the composition S1 and S2. So to find the composition of S2 and S1, which means that we are finding S1 circle S2, by definition, we're looking to all pairs of elements x and y such that we can find z, number z, such that x and z is in the relation S2 and y and z in the relation S1. Note that the order of the notations here is very important. So I want to find pairs x, y, so that you can find z, where x, z is in S2 and zy is in S1. After we write this definition very carefully and we know where is our notation r, now we look to the definition. So xz belongs to the relation S2. By definition, it means that the second coordinate z is equal to the first coordinates x squared plus 2. While zy belong to S1, it means that the second coordinates, which here is y, is equal to minus 5, the second coordinates, which here is z, plus 2. Now I want to write this relation as a relation of x and y, and what we need here is just to substitute z. So here we have minus 5z, and here we have z as an equation of x. So that means what? That means we want to all the pairs x, y, where y is equal to minus 5z, I replace z here with x squared plus 2. So it would be minus 5, x squared plus 2 plus 2. And now I expand this one. And when I expand it, will give me all the pairs x and y, such that y is equal to minus 5x squared minus 8. So I find the composition of the relation S2 and the relation S1 as all the pairs x and y, such that y, the second coordinates, is equal to minus 5, the second coordinates square minus 8. Similarly, if I want to find the composition of S1 and S2, that means I want to find S2 circle S1, and by definition it's all the pairs x, y, such that you can find z, where xz is in S1 and zy is in the relation S2. So writing the definition of S1 for x and z, I write in the definition of zy for the relation S2 and substituting that, we will find that as a result, S2 circle S1 is all the elements x and y, such that the first coordinates here is y is equal to 25, the second coordinate is square, minus 20, the second coordinate, which is here is x, plus 8. Here we give a theorem which relate all what we studied about the inverse of a relation, composition of a relation, and the identity relation. Thus the theorem says that suppose that A, B, C, and D are sets, and R is a relation from the set A to the set B, and S is a relation from the set B to the set C, and T is a relation from the set C to the set D. Then, if you want to find an inverse of the inverse of a relation, this will only give you the original relation. So if you want to find the inverse twice of a relation, it gives you the original relation. Also, if you want to find a composition of relations, here is the composition of R and S, and after that you find the composition of the new relation with T is the same as finding the composition of R with the result of the composition of S and T. This law here shows that the composition of relation is associative operation. Note that the relation R is a relation from A to a set B, so we can do the composition of the relation R with the identity relation on B, and the theorem says that this composition is a relation R itself. Also, R is a relation from A to B, from the set A to the set B, so we can have the composition of the identity relation on A with the relation R, and the theorem said this composition is the relation R itself. The last identity here we have is the composition of the inverse of the composition. So if I take the inverse of the composition of a relation R with a relation S, is the same as taking the composition of the inverse of S and the inverse of R. I will prove here the third one. I will want to prove that the identity relation B on B circle R is equal to the relation R. To prove something about relations, we have to remember that relation actually is just sets. So to prove that they are equal, we're supposed to prove each one of these sets is a subset of the other one. So I begin by taking a pair of elements x and y in the composition of this relation. As identity relation circle the relation R. What it means by definition that we can find z in the relation B such that xz in the relation R and yz is in the relation in the identity relation B. But we know the definition of the identity relation. So if z and y is the identity relation on B, that means z have to be equal to y. So replace the value of z here in the relation R, we'll find that xz is just equal to x and y, and this by hypothesis is equal, belongs to the relation R. So what we have, we take a pair of elements in the composition of these two relations, and we find this the same pair of elements in R. That means this composition is a subset of the relation R. On the other hand, if I take another element, a pair of elements in the relation R, that means B is in the set A and Q is in the set B, and that means Q and Q is the identity relation on B. And that means B and Q is in the composition of these two relations, the identity relation on B circle R. And hence, that means the relation R is a subset, as a set, is a subset of the relation which is a composition of R and the identity relation on B. So by these two, we find that this implies that the two relations are equal. By this, we end the fourth part, which explains all these topics about relations.